Okay, well, hi again. This talk is going to be as different as humanly possible from my last talk. This is what I actually do. So this is called a spectral framework for constraining anisotropic eddy viscosity. So this is from a paper that I'm currently in the process of publishing, and it's related to some pretty in-depth ocean modeling. It also relates very closely to work I've done in the past. So the subtitle, Using Tensors and Cascades to Make Eddy Closures, is sort of to motivate the mathematics that are going to go into this formulation that I'll present. And so just to give you all an idea of why I'm doing this and where it's going, for a lot of my career, I've been interested in mesoscale eddies and large-scale ocean modeling. It's pretty clear that there's a big difference between a non-eddying ocean model and an eddy-resolving ocean model. So, it's really a matter of just going anywhere between, say, 1 degree grid resolution down to about 1/10. And I can tell you in the about 10 years that I've been working on this problem, this used to be the only thing we could really do, or at least, in any repeated fashion. Whereas this was kind of out of reach. But in the last 10 years, we've sort of made the jump over to this middle plot where we're sort of at what we call marginal eddy resolving resolution or eddy permitting resolution. So there's different terminology for this. So we think of this as a Rand's or Reynolds average Navier-Stokes model where, if we're interested in parametrizations, we really mean that the eddy mean interactions are small or very weak. And so that's still quite easy to do computationally nowadays. The areas that we're starting to get more interested in, which is why I'm interested in turbulent cascades, are these ones we're going to call moles, or mesoscale ocean large eddy simulations. The idea here is that the eddy mean interactions in these models are quite significant because there's no real separation of scales. And so if you're going to build a parameterization of any kind, this is really a turbulence model, not a parameterization per se. Whereas if you're considering, say, mesoscale eddies, there's really no need to do any turbulence closures here because you just resolve them all straight away. We're still quite a ways away from doing this resolution modeling with any big frequency. And so I'm still saying this is not near future, but we're still in this zone where moles is the thing we want to think about. So it turns out eddy closures are really important. Here's an example from the Gulf Stream, or at least the Gulf Stream separation in the northeastern United States. This is sea surface temperature bias. And so you can see when you have a low resolution ocean, there's just this massive, say like up to 5 degrees C sea surface temperature bias off the coast, anywhere from New York up to Newfoundland. And part of that is because this resolution isn't really sufficient to resolve shelf processes or transport off the shelf. It keeps the Gulf Stream, or at least the return current, kind of in the incorrect position. We actually see these kinds of bad biases over in the Pacific as well. And simply by going to high resolution, you can fix these things pretty well. I mean, this is the change. And so the idea is that if the colors here in this plot match the ones in the top plot, then that's pretty much solved. And so simply by going to about 1/10 of a degree, we get all the requisite processes to fix some of these biases. And it really speaks to the fact that eddies, whether mesoscale or submesoscale, really control so much about not only the ocean circulation, but the distribution of tracers. Here's another slide just to kind of drive that point home. So here's just looking at sensitivity to grid resolution. This is from a low resolution CSM ensemble or community Earth system model. So again, these are biases. You can see that this blue thing here, I can't remember what they call it. It's like the blue blob of death or something. It's like this low SST bias just sitting out here in the Atlantic. You can see the difference you get, again, just by going to high resolution. You really start to concentrate some big temperature differences in places that you can imagine is very sensitive to model resolution. We tend to fix the blue blob of death pretty well, though we seem to get other blue blobs of death down here. But the point is that, again, high resolution eddies, especially mesoscale eddies, really run the show here. And so, again, to drive that point home, maybe one more time, this is the surface kinetic energy field. Again, moving from this 1 degree Orca 1 down to 1/12 degree Orca 0083. You can see all of a sudden, you get the Antarctic circumpolar current and all its associated eddies, the Gulf Stream, the Kuroshio. It's just really remarkable how different the solutions are. And if you looked at things like temperature, salinity, and all the other important thermohaline tracers, that you'd see sort of the same story occurring. So we'll take a moment to admire this wonderful movie. The lesson here is pretty obvious. The oceans are turbulent. Our models don't always have to be, and obviously if we're in that 1/4 degree to even 1 degree resolution, they cannot be, because the deformation radius is not really resolved in most places. But you really need to capture the effects of this stuff. Even if you don't have the turbulence explicitly represented, they're doing so much to control the distribution of basically everything that it's really crucial that you do the best job of modeling this stuff as possible. So looking at it from the perspective of equations, right? So I like to work with the Buscan-esque primitive equations. It just makes things easy. I know they're not exactly what we solve in our ocean models, but for this discussion, they'll be sufficient, right? So buoyancy is the key thermodynamic tracer. You get a buoyancy equation, not necessarily, or sort of similar to a density equation. The buoyancy itself is a small perturbation above the background, which is why we call it Buscan-esque. And it is a function of temperature and salinity given by theta and S, which are conserved, or at least to within some forcing term. So it's nice to work with this set of equations just because it keeps things easy. But if we watch this movie, so this is a movie of what we'll call lab scale turbulence, where we're really resolving down to the Kolmogorov scale. It's really beautiful. I mean, I don't exactly know which field we're looking at, but we're watching turbulence coming off of a box. And you can see so many different turbulent structures. This is quite inviscid, so there's really no control by the model viscosity here. But this is essentially, what these equations are truly describing. Now let's consider this one. All right, so here obviously we're looking at the North Atlantic plus the continental United States. Similarly beautiful. You see a lot of the same types of patterns, a lot of the vortices. Of course, the force balance here is quite different because we're at low Rossby number. So we have a little more propensity to form large-scale vortices, jets, Rossby waves, and things that we care about in geophysical fluid dynamics. But perhaps the important point of it's showing some hurricanes forming and coming over to cause damage. But perhaps the point to drive home here is that these are not actually the equations being solved in this model. This is a completely different scale, right? So like we're talking thousands of kilometers, not millimeters. And so the actual equation set is not this one, it's this one. So what do we see here? What we've done here is taken that same equation set and applied some kind of averaging or filtering operator. And so that's given by the overbar. Perturbations away from the average or filtered quantity are given by primes. Overall, the equation sets look quite similar, except we see that there are a couple new terms in these equations which arise from averaging the advection operator. And these are what we'll call the Eddy terms. And I'm showing this in the RANS framework. So again, Reynolds average Navier-Stokes. Just for simplicity, if we were in the moles regime, there would be a couple extra terms here. But the point to sort of digest in this equation set is that all of a sudden, by doing this little operation, we've got some new terms that we need to take care of, regardless of what model grid we're on. So it doesn't matter whether we're on a cube sphere or tetrahedrons or whatever. This is the Eddy closure problem. So the challenge we have, or the challenge that I took up in my past life as an ocean model developer, is how do you represent these prime terms in a physically sensible way that improves the fluid simulation? So that's kind of the subtle yet important point. And I'll expand on that a little bit. So improves the fluid simulation. There's a couple requirements. One is that your solution, whatever you do to model these terms, has to be performant, meaning that it cannot suck up a substantial fraction of your computation time. It has to be numerically stable, meaning that it cannot crash the fluid simulation if you do it whether right or wrong. Hopefully that it's not damaging. Hopefully it has as much fidelity as possible. And what I mean by that is, generally when we do studies of how to build these parameterizations, you want them to mimic that physical process as best as possible to calibrate and tune it. It's not strictly necessary that you do that. I mean, you could sort of stumble upon a good parameterization by accident, although in practice that never happens. But the bottom line is, does it make the model better? Coming from an institute where we do climate modeling, that's really the bottom line. I mean, people do kind of crazy things as long as it makes the model solution better, because at least with climate, we have very specific targets and very well-observed quantities that we're trying to hit. So this all boils down to what is a turbulence closure. A closure is something, and by something it could be a term, it could be a formula, a prognostic equation, an embedded model, a neural network, any number of things. And this closure is meant to represent and account for the effects of subgrid scale turbulence into a model where it's not sufficient to, or the grid resolution is not sufficient to resolve the turbulence. So sort of the goal, like I've just shown before, can we get the stuff in this model to behave a little more like this model? Again, obviously it's impossible when you jump a factor of 16 in resolution, but by parameterizing those prime terms, hopefully you can get the important stuff to match up as best as possible and improve the fidelity of the simulation with respect to whatever observations you may have. Okay, so let's talk about the recipe. And so I'm going to ask you, please pay attention to the green keywords that are going to occasionally pop up, because they're going to motivate what I talk about in the second part. Okay, recipe number one is make it simple. And this is really important because there's a million ways to make it not simple, and those don't help. And I'm guilty of writing at least one parameterization that is really not simple and no one uses it. Okay, so idea of making it simple, here's one example. We can use a Taylor expansion. So we imagine that we have some tracer tau, and we have some small perturbation to tau, and we'll just call it tau prime. And we're going to Taylor expand using very, very small increments of distance that we'll call L in each direction. So you have L prime sub x, L prime sub y, L prime sub z. And then the Taylor expansion basically says you can just multiply that little jump in distance against the background gradient, and that gives you a good approximation to your tau prime. So we have first order terms, we have second order terms, and we have so on and so on. Basically, the simplest recipe is to drop everything from second order and above, multiply by vector u prime, and then your bar average. And so you get something that looks like this. So you have your eddy flux term, u prime tau prime, is now basically proportional to your u prime L primes multiplied by the background gradient. And that gives you a tensor that we'll call K. So this is what we call a flux gradient relationship, where the proportionality is governed by tensor K. And it is, well, nominally down gradient, meaning that it has the negative sign up front. So that's really simple, and yet it is the recipe that I would say at least 90% of models use, and very successfully at that. The key word to take away from this slide is tensor, because we're going to definitely use those. You can do it a lot of different ways. So you can expand, for example, if you non-dimensionalize your equations, you can expand in Rossby numbers, but basically anything small. So the idea is that the increments tau prime and L primes are small. So that's essentially what you're expanding by. Okay. All right. Okay, so that was simple. This is a nice clean equation here. Okay, number two, part of the recipe is make it stir and mix, and we can watch this fun little video. So this is what stirring looks like. Apologies to anyone who is colorblind. I didn't have any control over this movie. But okay, we got green dye on the left, red dye on the right. And this person is going to do some very, very gentle stirring. You might get the impression that they're mixing together, but they are not. Okay, and now very, very gently reversing direction. This movie always blows my mind. I don't know how many turns. Not that many. All right, that is called reversibility. So essentially stirred it just gently enough to not irreversibly mix that stuff. Okay, so in terms of K, we can do that pretty straightforwardly, and there's plenty of mathematics in the literature to talk about this, but you can break K into symmetric and anti-symmetric parts. The symmetric part represents mixing, anti-symmetric part represents stirring. So that's nice. Okay, number 3, closely related to number 2, make it stir and mix in the correct direction. And this is a kind of confusing little graphic that actually points here. So example, anyone who's done ocean modeling may be familiar with the Reddy and Gent-McWilliams parameterizations, which are meant for mesoscale eddies. So I'll talk about this little diagram here in a moment. So here we have our material derivative of some tracer, theta bar. Here's your eddy flux term. Again, we have our flux gradient relationship here, which I'm starting to write in Einstein notation. We break it into symmetric and anti-symmetric components, just as so. So this is a mathematical identity. And the parameterizations themselves are essentially a tilted diffusion with the idea that in the ocean, the direction of least energy expenditure is along neutral density surfaces. And so the L's here are isopycnal slopes. Kappa is some mixing coefficient. And this tensor is essentially directing the mixing down gradient along one of these tilted surfaces. A, the antisymmetric part, is the Gent-McWilliams parameterization, which I would argue is the most successful eddy parameterization in existence, as evidenced by several thousand citations in the literature. So this can be written in a lot of different ways, but essentially this parameterization represents eddy stirring. It is advective transport. It does not mix, but it does homogenize tracers along density surfaces. Using some not too difficult calculus, you can write this as a stream function. And then the parameterization itself also uses isopycnal slopes and some different mixing, some potentially different mixing coefficient mu. So the diagram here is essentially showing what the Gent-McWilliams parameterization does, which is release potential energy by fluxing stuff slightly across the isopycnal slope so that it slumps these surfaces over. It mimics the actual action of mesoscale eddies, releases PE, and it does essentially isopycnal overturning. To make things a little more spicy, we've also thought about, well, what happens if you don't have a scalar mixing coefficient? What happens if you allow for anisotropy? And so we can sort of straightforwardly go from what was on the previous slide to this kind of fancier version where your mixing tensor now has these sort of subtensors, S sub h, where instead of one mixing coefficient, you now have 4, or I should say 3. The antisymmetric part, the Gent-McWilliams part, can do somewhat the same thing, where again, you have isopycnal slopes, but you can potentially have 3 different mixing coefficients, and that's to allow for the idea that maybe shear or something else takes your tracers in different directions at different rates. But the physics are the same. Again, it's a long isopycnal diffusion for the symmetric part, overturning advection for the antisymmetric part. And the key word here is anisotropy. So this is something I've played with in a couple papers in the past. I don't think anyone has actually employed this in a global ocean model, but we do have evidence that it could help. But for now, let's just remember this thing. Okay, so we have 3 ingredients. Let's get to the last one. Actually, no, let's not get to the last one. Let's talk about this one more time. Okay, so this seems not too bad, but there's a better way to look at this rather than these tensor coefficients. Can we simplify this problem? Well, yeah, we can, because this whole thing is really governed by just this one little 2x2 subtensor, right? Because that thing appears here, here, here. So you can do better. How about let's just study that little 2x2 instead of the 3x3? And actually, a nice way to study symmetric tensors is by eigenvalues. And so, we kind of know by design that what we did with this tensor is it's a strong isoneutral diffusion and a weak epineutral or cross density surface diffusion. And so you can actually show pretty straightforwardly that you can look at the eigenvalues here, which is a lot easier, and it would give you the same eigenvalues as looking at this thing, S sub h. It's just a good idea to do that because now you can boil it down to 2 coefficients rather than 3. All right, we've done that. And if you make a map of this across the ocean, it doesn't look great. It's pretty complicated, pretty noisy. You do have 4 different coefficients for this tensor K that you diagnose. The magnitude is all over the place, positives, negatives, and you don't know what to do with this. But if you break it down to eigenvalues, all of a sudden it becomes much more familiar. So the major eigenvalue, or the bigger one, you actually start to see your classic ocean structure starting to appear, right? So you got your ACC, your equatorial current, your boundary currents, and that starts to make sense. The minor one, maybe not so much, but again, it's minor, so that's okay. And you can start to make things like probability maps about how likely is it that you get a particular ratio of major to minor. And so again, this is all sort of building towards this idea of making a better parameterization by mixing at the right direction at the right rate. And eigenvalues are the way to go. So we can remember that word too, eigenvalues. Okay, and now number 4. We're starting to get into turbulent cascades because we need to make it stir and mix at the appropriate rate. So if you remember, this thing has some coefficients kappa and mu in it, and we don't know what to do with those. But this is what you can do. So this is all about estimating an appropriate mixing rate, and the turbulent cascades really give us a nice handle to do that. In fact, I would actually argue that being in the eddy permitting realm of like 1/4 degree or higher is a lot easier than the RANS realm because we can actually use this. So the idea behind this approach is that we expect a marginally resolved turbulent cascade, meaning that we have just enough eddies in the model to see some real turbulence and transfer upscale and downscale. So the idea is, since we have some turbulence, we can remain faithful to it and tune our parameterization. So this is a classic schematic. So on the vertical axis, we have summit invariant. It could be energy, it could be entropy, it could be something else. On the horizontal axis, we have wave number. So this dashed line will be at the high wave number end. So this will represent the smallest available scale in your model. And you're forcing somewhere in here, and that invariant is either cascading upscale this direction or downscale this direction. Really, dissipation should happen way, way down here, but we're not going to get there because our model can't resolve it. So again, high wave number end is down, low wave number end is up. Okay, so from a modeler's perspective, the following things are possible. So you could give the model, you could assign the model a viscosity, and therefore determine the dissipation scale, and so therefore your model becomes a direct numerical simulation. So this is what you'd see if you're doing turbulence in a box, and you say, I'm going to tell it to have Reynolds number 1,000. Well, you give it the viscosity, and you know your dissipation scale, so you can calibrate your model or your domain appropriately. What we're going to do, though, is for a given dissipation scale, meaning that we want it to be at the grid resolution, we can give it the appropriate viscosity. And so we're going to do this in QG realm because, again, this is a GFD conference and that's what we like. And so, again, this is moles, this is mesoscale ocean, large eddy simulation. We have a couple requirements that I've glossed over a little bit, but here's a couple extra ones. So one, it has to be scale aware, meaning that it should not really matter whether you're at 1/4 degree, 1/8 of a degree, 1/16, or whatever. It should tune itself up and down or turn itself on and off appropriately. Don't double count, meaning that you have turbulence already. You don't want to add on more than is necessary, such that you get twice the effect when you don't want it. Don't half count, meaning that your parameterization has to do something. Don't make it too weak, so that's pointless. Obviously, don't blow up. You don't want to crash your model just because you put in a fancy new parameterization. And then sensible boundary conditions, one that people don't really like to think about because it's really hard, but if you're going to bump up against land, you don't want your parameterization to do something stupid. Okay, and so an LES style approach would basically do the following. So we have a turbulent cascade. You have a dissipation rate, right? Because it's generating stuff, and that stuff is going down to the grid scale and then disappearing. So you know the dissipation rate it needs to have. And so you can basically tune your eddy viscosity such that this is the new Kolmogorov scale, at least for the 3D turbulence. And that is the entire essence of, perhaps you've heard of Smagorinsky. You can do that with 2D turbulence too. So now you're cascading entropy downscale. It would be dissipated down here at the bachelor scale, or I think that's bachelor scale, yeah. But instead you want to dissipate here at the grid scale. And so you give it, again, appropriate viscosity. And the part I think we're most curious about is what to do in quasi-geostrophic turbulence. Qualitatively and quantitatively very similar to 2D turbulence, but again, you're getting potential entropy cascading downscale that you want to dissipate here. And so you give it the right tuning. This is what it looks like. So here's your classic LES closure, Smagorinsky, probably the most well-known turbulence closure in 3D turbulence. So you can see you're basically giving it an eddy viscosity that is proportional to grid scale squared. And here's the deformation rate. 2D turbulence, notice that your grid scale dependence is different now. Now you have a delta x cubed. And instead of the deformation rate, now you just have the gradient magnitude of vorticity given here. And the newest one, which was a couple years ago, we did this for quasi-geostrophic turbulence. Again, looks really, really similar to 2D, except now you have the quasi-geostrophic potential entropy, and you've got some new terms, such as the vortex stretching term, and then beta. We actually threw this into a global model, and it did some cool stuff. So not surprisingly, QG turbulence is very similar to 2D turbulence plus a couple extra terms. Not surprisingly, those extra terms give us a little extra viscosity. So it does look different than 2D. This was really surprising is that, again, we're claiming that this is an appropriate way to scale viscosity for these types of models. And it turns out that you can actually get smaller scale structures using this approach with harmonic operators than you can with biharmonic operators that are tuned naively. That should not necessarily be the case. Biharmonic operators operate at wave number to the 4th or higher, whereas this only operates at wave number squared. So you'd think that it would be reversed, but it's kind of neat to know that appropriate tuning does this. We looked at a lot of other things too. I think the most interesting thing to take away from these slides is probably given up here. That compared to biharmonic friction, so here's the PDF of the dissipation. We're dissipating less than biharmonic did. So basically we shifted these PDFs over to the left. But what ended up happening instead is that we actually moved that dissipation over into bottom drag. And so maybe that's not surprising, but it's kind of cool that the model needs to dissipate energy somehow. And so even if you tell it to dissipate less via viscosity, it will find a way, and therefore it'll actually shove a lot of that energy dissipation into the bottom. Whether that's a good thing or not, we're not totally sure, but it definitely has a strong control on things like circumpolar transport, as well as other stuff, like the overturning circulation. Okay, but that little aside was really just to give you a new keyword, moles, or mesoscale ocean large eddy simulation. And those are the keywords. So we had tensor, we had anisotropy, we had eigenvalues, and we had moles. And that leads into the new stuff. So we're ready for anisotropic viscosity. Okay, before we dive in, I think there's some cool stuff to talk about here. So first of all, the brief history. This idea was actually introduced by Richardson himself over 100 years ago. And there's a line in this book that he wrote. The general theory of anisotropic viscosity is found to be ready-made in connection with the elasticity of crystals, which is really a generalized Hooke's law. That's not really surprising. I mean, Hooke's law is what eddy viscosity is based on, but he was thinking about it in terms of, say, a general stress-strain relationship in a solid. It actually took about 40 years for this theory to even start trickling into atmospheric sciences, and then it wasn't even until the 90s before it appeared in the ocean modeling literature. The last papers to talk about this were by some big names about 20 years ago, but it has not been touched, really. And this idea was actually tested only once by my colleague Bill Large in 2001. And their idea was that they were running CESM in a global ocean simulation, and it was at like 1 or 2 degree resolution. So they had this really horrible equatorial current because it was just too diffuse. And so they thought, hey, let's dissipate less across, in the north-south direction to get that equatorial current to be a little sharper. And it actually helped. So they got excited about it, but then, of course, it never appeared again, so that's too bad. But, this topic has been bothering me for a while, and, we actually need eddy viscosity, so why not? Let's take a look at it. It turns out there's a good reason why not. It's like it's really hard. So the problem is that the math is really opaque, and there's a lot of uncertainty that I'll talk about here. So I already showed Jen McWilliams and Reddy sort of as the comparison point. This is what that looks like. Again, we've seen this before. So here's your eddy flux, here's your down gradient, flux gradient relationship. You have symmetric and anti-symmetric parts. You have a couple degrees of freedom, depending on whether you're in 2D or 3D, so 4 and 9. It actually turns out we do have some constraints that make this a little easier, so it's not so bad. And we can actually diagnose this, as I did in one of my previous papers. For isotropic diffusion, yeah, we totally can. And for anisotropic diffusion, we can get pretty close. We can do it for the symmetric part, but not for the anti-symmetric part. This is the problem. For anisotropic viscosity, the math gets way worse because we do have a flux gradient relationship. However, A, which is the new thing, or I'll call it fancy A, not this A, this is a different one. This is a 4th order tensor, which makes it way harder. We have to use Einstein notation pretty much exclusively because there's so many indices floating around. We have some sensible but sort of obscure rules about how this should go. So because this stress tensor is symmetric, we get this symmetry here. We believe that there should be no stress for pure rotation. So if there's no shearing, then nothing should happen. So that gives this set of symmetries. We want the ability to force the tensor to give us sign-definite dissipation. So if we tell it you have to dissipate energy, then that forces this constraint on us. And this last one, which I'll talk about in a second, is called the deviatoric stress requirement, and that gives us this. There's way more degrees of freedom. Normally, in this guy alone, you have 81 degrees of freedom, but you can boil it down this far using these symmetries. You still have not enough constraints to do anything with it. Is it diagnosable? Kind of. With isotropic, yeah, but it's really ugly. And anisotropic, no. So it's just a hard problem. The math gets really deep into the basic fluid mechanics. So for example, I'm going to start with what we call the constitutive relation, which basically says the change in the velocity along a material line is the divergence of a stress. You can break that stress into a compressive part, which we'll call the thermodynamic pressure. That's pretty familiar. And then this deviatoric part, so tilde tau. Tilde tau, we'll write it like this. And we're going to make the following assumption that we're hydrostatic enough that we can chop up this stuff and just break it apart. So basically, we don't want to handle anything in the vertical direction because that's not what we do anyways in ocean models. So we're only going to worry about the horizontal parts. And as I said before, this is called the deviatoric stress. So basically, we're only worried about the case when this little subtensor has zero trace. The reason for that is that any part that does have a trace, you can just throw it on top of the pressure and then make it go away. So it's sensible to do this trick and it'll make our lives a lot easier. Note also that if you did Reynolds averaging, this turns into U prime, which we've seen before earlier in the talk. So this isn't some obscure thing that I pulled out of thin air. This actually relates to the Reynolds stresses. Okay, so what do we actually do with this? So here's a 2D example. So we've got our stress on the left, strain rate tensor here. This is our viscosity tensor we want to parameterize. Normally what we do is an operation called unrolling, which is to say, note that this is not, so this is similar to a matrix vector product, except it's generalized to higher order. So this is a fourth order tensor, this is a second order tensor, this is a double contraction operator. So it's very similar to a dot product except higher order. Again, like you can't really visualize the math here, but you can do this thing called unrolling where you write it instead as a vector matrix product. And so by doing that, you can see all 16 elements of A are just sort of written out explicitly here. The E dot components are over here, the stresses are over here, so it makes it just a lot easier to understand. Again, we got a lot of symmetries that we're imposing, and that changes some things in a good way. So what we get after applying all this stuff is that you actually have two constraints over here. Notice that these ones are redundant. And you have three unique unknowns. So again, if you look around this tensor, you'll see that these guys are repeated everywhere. So that's a lot simpler already. It's not 16 unknowns, we're down to 3. So that's nice. Okay, so you do a little elimination of redundant rows and columns, and then you boil it down to this. And you do a little trickery. So one thing we like to do, at least in ocean modeling, is we like to use these variables instead. So this is known as the shearing strain. This is the tension. This is the divergence. These are the associated quantities in terms of the stress. And so using a little rewriting just for brevity, this is actually the thing that we throw into ocean models. So normally we have what's called isotropic viscosity, where this guy and this guy, alpha and beta, are non-zero, the gammas are 0, and this is what you actually see if you look at ROMS or MOM6 or MIT GCM. So this is a mathematically robust way to do it. So notice it did not really help us in terms of the constraints and unknowns, but it did boil it down a lot. Notice that we have a 0 across here in the middle of the tensor and a 0 along here. That's from the deviatoric condition that we put on. And so, okay, this isn't bad, or well, it is bad, but it's not that bad. We're still stuck with this problem that we have more unknowns than constraints. So unrolling helped because at least it let us look at it, but did it help with our physical intuition? I would argue no. But yeah, I mean, it is cleaner though, so what can we do with that? Okay, so mathematically what we actually did there with this unrolling is that, I'll just write it like this. So anything with a subscript V is this Voigt notation unrolling. What we actually did was we created a mapping that takes these tensor indices and remaps them to something we can actually visualize using a 2D matrix. So this is a mathematical operation, casting, basically it's a function that takes your tensor from this geometric space to this geometric space. and the same for second order tensors to vectors. So A, our fourth order tensor, became a V, which is now this little matrix. The stress tensor sigma became sigma V, which is now just a vector. The strain rate tensor became E dot V, which is again just a little vector now. However, there's a hidden pitfall here, which is that the differential geometry ends up being really nasty. So that happens because the strain, the stress, and the tensor itself are sort of a mixture between covariant, contravariant, and both components. And the tensor basis we actually use to do this is not normalized. We don't need to get into any deeper into the differential geometry of that, but the bottom line is there is a mathematical reason why you get this weird discrepancy between what happens to stress and what happens to strain. Notice the strain has this little extra factor of 2, and that's going to kill us. Okay, so why does it matter? Before we get back to that, there's a reason I'm doing this. So one is I introduced this keyword eigenvalue earlier, and it turns out that eigenvalues have higher order generalizations. So this is, your usual eigenvalue problem. You have a matrix, you have a vector, you have an eigenvalue. Now you have a tensor, you have another tensor, and you still have an eigenvalue. It's just got a double contraction, but the idea is the same. Eigenvalues are good. They make life easy. The dissipation, so this is a strict identity. The dissipation is given by this object. When we unroll, when we write this whole nasty thing out in terms of second order matrices and vectors, the question is, does this identity still hold? Because if it did, if you look at this condition, so you got vector, matrix, vector, forcing it to be greater than or equal to 0, that is the definition of being positive semi-definite, which is sort of a well-known linear algebra topic, or at least idea. The eigenvalues control this. So again, the reason I want to do this is because if I can do this thing with unrolling, then the eigenvalue properties hold, and I can actually enforce everything about this anisotropic viscosity through eigenvalues, which is really cool. Okay, so the question is, I need to unroll this tensor so I can see it, but does that eigenvalue stuff actually work? Not really, unfortunately. So the basic identity works that, by design, the double contraction reduces to a dot product. However, these identities don't hold. So if you multiply the strain by the strain, that doesn't work anymore. If you multiply the stress by the stress, that doesn't work anymore. And that's because we had this bad differential geometry thing. We get the Newtonian law to work, but we don't get the inverse. Also, you get this property, but the eigenvalues don't work. And so it's kind of a mixture of nice check marks and sad faces. We got close, so we're almost able to enforce this dissipation requirement through eigenvalues, but the problem is that when you do this unrolling with the Voigt way, your eigenvalues of A sub V are not the same as the eigenvalues of A, so that kind of is too bad. But there is a solution, and this is kind of the novelty of this work I've been doing. There is a different notation called Mandel notation that fixes that problem. So there's a simple transformation you can do to the Voigt unrolling, and it really has to do with just throwing a little square root of 2 down here. And that'll actually take everything, normalize it, such that when you unroll into Mandel form, you actually get square roots of 2 kind of floating around. But notice that when you unroll the stress and the strain, both of them have a square root of 2 sitting down here in the third element. Again, our tensor basis is orthonormal. That fixes all of our problems. And so all of these identities that I want actually work now. So work conjugacy works. We can actually recover the notion of an inverse of a fourth order tensor. So again, like C double dot A is equal to some identity tensor, which is really cool. The dissipation maps onto itself, which is great. The eigenvalue problem maps onto itself, which is super great. Orthonormality works. So if you have two tensors that are orthonormal to each other, that also passes over into the unrolled form. And so that's wonderful. That enables everything good in the world to happen. So it means that the dissipation, the sign-definite dissipation can be controlled through eigenvalues, and that's the thing I'm going to use. So notice these two forms side by side. Voigt is over here, Mandel's over here. Again, you just have square roots of 2 sprinkled throughout. You can rewrite this in this different form. So this is the form we want. It worked with Mandel. It does not work with Voigt. That's kind of coincidence, and I'm not going to apologize for it. Eigenvalues are generally not preserved when you do row operations to get from here to here, but in this case they are. So let's be explicit about that. And it makes everything really simple because this is a super simple tensor or matrix. The eigenvalue problem is really simple to calculate. You have identities such that the sum of the eigenvalues is the trace, the product of the eigenvalues is pseudo-determinant. The eigenvalues are given by this identity. And it gives us a whole different set of conditions. So for example, previous work has argued, hey, these are the requirements you need for sign-definite dissipation. You can kind of do that just by brute force, just by multiplying this thing out, which is what you get there. But if you do it through the eigenvalues, you get a much less strict set of conditions that still allow you to get sign-definite dissipation. And you can actually confirm that if you just plug it back in and run through the problem. So this is the new thing. This is the old thing. This is actually really attractive, and I'll show you why. So it introduces a lot of questions. So one, that off-diagonal term gamma can actually be negative, and you can still get positive dissipation. The eigenvalues tell you explicitly what you're doing. So positive eigenvalues mean you're dissipating energy. Negative eigenvalues mean you're backscattering. And you can actually mix the two. So you can have a tensor that gives you both dissipation in one direction and backscatter in another, which is kind of wild to think about. Apparently, gamma can be negative, and the eigenvalues don't really care, which is really weird. I don't understand that, but it's kind of interesting to think about. The only other time this idea has been tested, again, without eigenvalues, this was just kind of like brute force. I hate to say Bill did the math wrong, but he did. And he only threw in these terms, and it kind of worked, but this is a much more general way to look at this problem. And so it'll be kind of interesting to try it. The last part we need to do is just to come up with some framework where you can actually test this stuff. So one nice thing just to clarify is that you can go back to isotropic scalar viscosity just by using nu like we normally do. This is familiar, this is familiar. So it does reduce back to something that we're comfortable with. But if we want to create a testing framework, you can do a little bit of statistics and actually make the argument that you can test a bunch of different possibilities for your viscosity tensor, and they will produce the same dissipation as long as you keep the sum of the eigenvalues the same. And so the end of the story here, I haven't actually tested this myself because it's kind of a big project and I don't have the capacity to do it right now, but you can actually create this little testing framework where you just say, okay, take every possible tensor you want, just make sure that the eigenvalues are the same across all the different things you test. You can set the eigenvalues based on that moles stuff that I talked about earlier. And you can just vary these other two parameters. Again, alpha, beta, and gamma are just these little things sitting across the tensor. You can just vary these two quantities, A and B, and just see what happens. And the nice thing about these is that they're bounded, they're well-defined in terms of what they're doing. You can reduce to isotropic viscosity, and there's an easy way to make this something that you can code into a model, which I've done in MOM6. Really simply, and just add a couple new parameters. And this is the way you need to be doing anisotropic viscosity. So it's kind of just sitting out there waiting to be done. Where does this leave us? We have not solved the problem of being underdetermined. Like, we still have more degrees of freedom than we have constraints, but it does let us understand what that tensor is doing. And so we can actually come up with a way to test all this stuff and just run through all the possibilities. You know, little caveat, this is a picture from one of our simulations in the model called Neverworld 2. Dissipation is given by positive values, so that would be like yellows, and backscatter or energy injection is given by blue. Unfortunately, the ocean doesn't really behave how our models want to behave, meaning that in a real eddying simulation, you get both energy injection and dissipation, and it just varies all over the place. So you can't really match this against observations, so this is purely a numerical construct that we're building. But there's still this really open question about whether this idea of anisotropic eddy viscosity could do something good. You know, it's been tested before, it has done something good, but generally, like, what do you do with this? And that's totally an open question. It also clarifies for us what backscatter actually is. It's negative eigenvalues, not necessarily negative coefficients of your viscosity tensor. So this is something you could totally play with, and I know backscatter is kind of a hot topic amongst a lot of modeling centers. So just let's be clear, these are about the eigenvalues of your viscosity tensor. But yeah, that's it. Conclusions, it took a lot to build up to here. You know, it required a new type of notation about how to write these things, a new way of thinking about anisotropic viscosity that's sort of informed by what we've done with diffusion. It's all about eigenvalues. And there's so many possible ways you can mess with this to emphasize dissipation, backscatter. We don't even know what best choices are, but that's an open research question, and this whole thing is currently under review. So thank you all. I hope you didn't get too much whiplash going from my first talk to this talk, but yeah, thanks for listening.
We might need to do short questions, but
No worries. Everybody leaves.
I was wondering, what's the relationship between this anisotropic viscosity
James,
and
can you use the microphone?
Yeah. Hello, hello. Okay. I was wondering, what's the relationship between this anisotropic viscosity and the map of the diffusivity? I think you had a diffusivity tensors map from on a global high resolution simulation.
Yeah, it's not related at all.
Okay, it's not just we're not doing a similar sort of rotation of diffusivity tensor or something.
No.
Okay.
Yeah, the map that I showed is for essentially isopycnal diffusion, and that is something that you can diagnose directly from a simulation. What I showed here with viscosity is not diagnosable. It's more just like showing like the mathematical ideas that you'd have to do if you wanted to just like test this using brute force. Okay. So it's not something that you can inform using high resolution models.
Okay, so yeah, thanks.
Yeah.
Maybe we'll, if you have questions that you can think of later, then find Scott around, pin him down to get the full explanation. And I think we should move on to Ivan's talk.